We're doing a second derivative implicit equations. So that means basically that we'll have x and y together, and that we'll be doing a derivative on y inside our function. But we have some tools to kind of help us get through this. So here's our function. Let y to the fourth plus 5x equals 11. And they want what is the value of the second derivative of y with respect to x at the point 2, 1. So this is my x, this is my y, and then they want an exact number. So the technique we'll use here is second derivative is you're doing the derivative twice, but it's going to be more complicated and more drawn out if we have the y kind of embedded inside the problem. So we have enough skills where we can get y by itself here, that we don't have more than one y. So we'll get y by itself, and then we'll do the derivative that way, and then deal with the second derivative as it comes. So y to the fourth plus 5x equals 11. So we're solving for y. I'm going to go ahead and subtract 5x from both sides. Y to the fourth is equal to 11 minus 5x. Fourth root to both sides. So fourth root is going to be the same thing as 1/4 power. So since we're in calculus, it's going to be easier that way. So y to the fourth root, or 1/4 power, that'll undo it, equals, and we'll do that to the other side, 1/4 power. So this will make it easier for us to do the derivative on it. So now we have y is equal to 11 minus 5x to the 1/4 power. All right, so we'll go ahead and do the first derivative on it with respect to x. D dx of y is equal to the derivative of the outside function is 1/4, 11 minus 5x. Subtracting 1 from 1/4 leaves a negative 3/4. Okay, that's the first derivative. Don't forget chain rule. So times the derivative of the inside, looks like a negative 5 pops out of there. Good, almost forgot. So there's our derivative of the outside function times the derivative of the inside function. And I'll go ahead and just simplify it a little bit. So this is dy dx. And the negative 5 will go in front. Negative 5 over 4. 11 minus 5x to the negative 3/4. Now, negative 3/4 would throw this in the bottom, but it's easier if we just keep it the way it is, so we can just apply the derivative to it. All right, so there's that. We'll go ahead and I'm going to just clean some of this off. Use this space right here. All right. So now we're on the second derivative, d2 dy dx2 is going to be equal to, so we have our negative 5/4 in front times the negative 3/4 times this function right here, 11 minus 5x. And we're subtracting 1 from negative 3/4, which is negative 4 over 4. So that's negative 7 over 4. So this is all to the negative 7 over 4. And all of this times the negative 5 from the chain rule. Okay. Let's see how we want to deal with this. Once again, this is our x, this is our y. Plugging it in right now looks like we don't even need the y component. We're just using the x equals 2. So that's going to be a 2 right there. And I'll just combine what I can. So this is a negative 5 times 5. Negative 5 is 25. Times 3 is 75. So I got a 75, and there's 3 negatives, so that's going to be negative 75 over 4 times 4 is 16. And this is going to be 11 minus 5 times 2, all to the negative 7/4. All right. So simplifying it some more, we have negative 75 over 16. That's negative 10. 11 minus 10, yay, is just 1. I was worried about this one right here, negative 7/4. All right, so that flips it to the bottom. The 4th root of 1 is 1. The 7th power of 1 is 1. All that turns into 1. And negative 75 over 16 is all we have left. Yay. Negative 75 divided by 16. Got it. Okay. So the technique for this one is solve for y first, then the derivative is going to be easier to perform on it, and the second derivative. Okay, next one. All right. Find an expression for d2 y dx2 in terms of x and y. All right, so let's go ahead and apply what we can here. It looks like we have a quotient rule going on, so it's always good to remind ourselves. D dx of a f over g function is going to be the derivative of the first times the second minus derivative of the second times the first, all over the second, or the bottom squared. When I was saying second, I meant bottom. Okay, so when we do the derivative, the first derivative here, we are given that dy dx is this right here. Find d2y dx2. Let's go ahead and apply it here. All right, so it's already given us dy dx equals x over y. We're going to do the second derivative on this. So d2y dx2 is equal to the derivative of the top is 1 times the bottom is y minus the derivative of the bottom is dy dx times the top, x, all over the bottom squared. Derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. Now, notice that we have a dy dx inside of our function. So the trick we use here is that we've already calculated, or it's already given to us, the dy dx, and we substitute it in. There it is right there. So dy dx is really x over y. And we just plug it in. All right, so we're substituting that in. We got y minus x over y times x all over y squared. Looks like it's going to be an algebra technique here. So I got y minus x squared over y squared. How would I do this is I would, I want to combine the tops first. And I don't know. I'm just going to go ahead and try it. I'm going to go ahead and each one of these is divided by y squared. So this is really y over y squared minus x squared over y squared. Now, my technique, and I know a lot of us kind of struggle with that, is I treat the middle fraction bar as a divide sign so that I can figure out how to combine these accurately. So this is really, so I'm just going to go ahead and do some side work here. Side work is that x squared over y divided by y squared over 1 is x squared over y times 1 over y squared, which is equal to x squared over y cubed. Okay, so all this turns into we got y over y squared minus x squared over y cubed. And we want to put these, let's see. So I can reduce out a y here. It's not going to help me because of this y cubed. I'd like to keep everything with a common denominator. So I'm going to go ahead and multiply top and bottom by y on this first one. So I have a common denominator. So that's going to give me y squared minus x squared all over y cubed. Okay, so this is y cubed on the bottom, y cubed on the bottom. So the answer has y cubed. This is y squared minus x squared. Okay, so this is as simple as I can make it for d2 y dx2, second derivative of y. Let's see how we did. So the trick here is substituting in what dy dx is equal to get that out of the equation. So I got y squared minus x squared all over, let's see, how do I want to do this? All right. No, doesn't like that, does it? So I'll go ahead and just start over. Start with my fraction, y squared minus x squared all over y cubed. All right, let's see how we did. Everything looks like it should. And we got it. Okay, good. So that's kind of the technique that we're using here, is that we're subbing this one back in if we see dy dx pop out into our second derivative.